Hello and welcome back. So right now we are on this topic centering, and in the past couple of classes we have discussed about the basic fundamentals of the centering process, and we have seen that the centering process is actually driven by atomic diffusion. So we have also discussed a little bit about the diffusion process as such, as to what is diffusion, what are the mechanisms of diffusion, and so on in the last class. So today we are going to continue on this topic. So one thing that you would have seen, as I just now said, is the fact that diffusion plays a major role in the centering process, in the sense that the matter which is to be transported to the neck for it to grow happens by this process. And we have also seen that there are well-defined paths for the diffusion process to happen during the densification. So apart from those paths, there is one more thing which plays a role in this densification process, and that is the curvature of the surface of the particles. Okay, so that is what we are going to discuss today, and then again we'll come back to this centering process and we'll see how the curvature is correlated with the densification that happens in centering. So let's say we have two phases, alpha and beta, separated by a curved interface, okay, like this. This side is alpha, this side is beta, and this is the interface which separates these two phases. Okay, let the volume of the phase alpha is V alpha, and that of phase beta is V beta. Okay, we are also going to use a set of terms, so let me first define those terms before we proceed. We are going to use P as pressure, and V as volume, and then we have some thermodynamic terms such as F, which is the Helmholtz free energy, G, which is Gibbs free energy, omega is thermodynamic potential, mu is chemical potential, So these are the terms that we are going to use, and if there is any more, I'll define that. So let's come back to this. So these are the two phases that we have here, alpha and beta, separated by a curved interface. So now when you have an interface like this between any two phases, any thermodynamic property can be represented as the sum of the bulk, that means the property of these two phases, alpha and beta, and that of the interface. So let's say any thermodynamic property, such as, let's say we call that as phi, which could be any of the thermodynamic properties, that could be represented as the sum of the thermodynamic properties of these two phases, alpha and that of the interface. Let us call that interface as sigma. So therefore this will be given as phi for alpha, for beta, and that for the interface sigma. Okay. Now these two terms that we have here, Gibbs free energy and Helmholtz free energy, let us define these two terms and then we'll proceed to the curved interface. G is given as U plus PV minus Ts, where U is the internal energy and S is entropy, T is temperature. And the Helmholtz free energy F is defined as U minus Ts. F basically represents the reversible work in a system at constant temperature, volume, and chemical potential. Okay. Now let us consider a thermodynamic potential which is represented by this omega. So this is given as F minus G, and if you substitute G and F over here, you will get omega equals to minus PV, right? So therefore for the three entities that we have alpha, beta and the interface sigma, we can write this term for each of them. And omega is also expressed as f minus sum of the chemical potentials when you have a number of components in a system. So mu I is the chemical potential of the ith component and Ni is the number of moles of that particular component. So this one is basically the Gibbs free energy. Okay, so that's how you have omega equals to f minus g. Right, so let us come back to this. When we say that any thermodynamic property is the sum of the properties of the phases and the interface. So here we can write for the thermodynamic potential as the sum of those three quantities, that is the thermodynamic potentials of alpha, beta and the interface. Okay, so therefore this quantity, the interfacial quantity, can be written as this. So to create this interface, you need the surface energy, because a surface is created now. The interface is basically a surface. So this thermodynamic potential will be actually given by that surface energy, if we call that as gamma, and the area, okay, the area of the interface. So here gamma is the specific surface energy, that is surface energy per unit area, and A is the area. So this is the total energy which is actually needed to create the interface, right? So omega sigma, that is the omega for the interface, is basically the surface excess. That means to create that interface between two phases, you have this surface coming, and as I said, gamma is the energy or the work required to create a unit area of that surface. So now if we come back to this can be rewritten as Now at constant V, T and mu, constant volume, temperature and chemical potential, the change in omega by an infinitesimal movement of the interface is null. What it basically means is d omega is 0. Okay, so if we differentiate this equation on both the sides and use this condition, then we will have this equation. Okay, and now here V is constant, so we can say that V is equal to V alpha plus V beta, and V is constant, so dV is 0. Okay, so we can write from here we can write this, and therefore we can say that dV alpha is equal to minus dV beta. Okay, and now we take this equation and here we replace dV beta in terms of dV alpha, and if we do that, this is what we will get. Right, or if we rearrange little bit, we'll get this as as this one, and from here we can write that P alpha minus P beta is equal to gamma dA by dV alpha. So this dA dV is nothing but the curvature of the surface, and if we call that curvature as K, we can simply write dA dV is equal to K, where K is the average curvature of the interface. Right, so from here, if we replace K over here in this equation, we'll get this P alpha minus P beta equals to gamma K. And if you have a curved surface like this, okay, so if you have a curved surface like this where R1 and R2 are the principal radii of curvature, then K is given as 1 by R1 plus 1 by R2, right? So a generic form of this for any given curved surface with radii R1 and R2, this equation can be written as and this is the well-known Young-Laplace equation. It basically describes the stress on a curved surface. Now the vacancies and atoms beneath a curved surface will have their own chemical potentials, and this chemical potential can be altered by the curvature of the surface. And this change in the chemical potential can be shown to be as follows. For the vacancies, it can be given by this expression over here. Where mu v is the chemical potential of vacancies, mu v naught is a reference value against which the chemical potential is generally measured. P is the mean hydrostatic pressure in the crystal just beneath the surface. Gamma S is the specific surface energy. VA is the atomic volume, and CV is the concentration of vacancies. Similarly, the chemical potential of the atoms can also be given in a similar manner. Here Ca is the fraction of lattice sites occupied by the atoms in the crystal. So Cv and Ca are generally very small, and therefore you can see that the chemical potential primarily depends on the hydrostatic pressure in the solid and the curvature on the surface. Okay. So now the powder particles which are being sintered also have their own curvature, and that will lead to a change in the chemical potential which will drive the diffusional flux, and as a result of that the surface curvature also acts as a driving force for the sintering process. So this is something that is relevant for the sintering process also, and in the next lecture we are going to discuss as to how this is related, and how the curvature is relevant for the sintering process or the densification that happens during the sintering process. But for today this is all I have. So before we finish this, let us take a moment to summarize this lecture. So to summarize, we can say that the curvature has a role to play in the densification process that happens during sintering. So we can derive the pressure or the stress which is generated due to the curvature. So that is what is going to play a role in the densification process. And this we have done today with the help of this diagram, where we have considered two phases alpha and beta separated by a curved interface sigma. And for a scenario like this, any thermodynamic property can be taken as the sum of the properties of the phases and that of the interface, which you see over here. And from that, considering a thermodynamic property called thermodynamic potential, we derived this relationship between the pressure and the curvature of the surface, and from here you can actually go to the Young-Laplace equation, which basically talks about the stress on a curved surface due to the curvature. Okay, so with that we come to the end of this class. Thank you for your attention.